This one is going to stretch my mathematical abilities to about as far as I can go. There's actually circles in here, and that's pretty much it for me, so bear with me on this one. The title is Accelerating Clocks Run Faster and Slower. And again, I don't believe in time dilation, and I don't think clocks run at different rates. I never believed that, but then I came across a website, which, well, I'll talk first. I came across a website where I saw someone saying clocks can run faster and slower if they're accelerated. I never thought about accelerating clocks. It's always constant speed inertial frame clocks. So I started reading this and looking at some of the arguments and things, and I said, this might make some sense, because I know if I'm on the metro down in Washington, D.C., and we accelerate, I start going backwards, you decelerate, and I could say, I could actually picture if I was a clock with a pendulum, and I'm going along at constant speed, nothing happens. Once the train gets up to speed on the metro, I'm holding on, everything is fine, and then it slows down and you start falling over. I said, well, gee, if I was a pendulum or something, I would start shaking around. Maybe acceleration is different for the rate at which clocks run, not time. Time doesn't change, but at least clocks. And so I started reading this website a little more, and like with the other things, I went off on a little adventure, did some calculations. I say these were probably, this is going to tax the extent of my calculational ability. Einstein's relativity, time is measured by clocks, slows with increasing speed, becoming especially noticeable as the speed of light is approached. And if you believe in black holes, time stops, and all the implications of that are from movies like Interstellar, which, by the way, I like, but is science fiction. Discussion usually focuses on constant speeds, although near the speed of light, and phenomena such as muon decay, or light speed, the Hafele-Keating experiment at much slower speeds, just airplane speeds. And these are, of course, proof of relativity, sacred tenets, and the mainstream moves on. Dissident scientists often contend that time remains invariant, although clocks may appear to run slower at increasing speeds. I know there's a lot of people who do accept that clocks run slow in inertial reference frames as they approach the speed of light. At least one such scientist contends that accelerated clocks can run both slower and faster, an interesting departure that I decided to examine being some examples. Don Sprague, I don't know if he's a member, but he has a website called Complex Relativity. Clocks lose time, but also gain time. Since Einstein predicts that time slows with movement, the Hafele-Keating experiment refutes Einstein. The clocks in the Hafele-Keating experiment show both a time loss and a time gain. Thus, the time gain portion goes against Einstein. The clock gain and loss is accurately predicted using classical mechanics and what he calls classical hierarchy relativity with relative C, because classical hierarchy relativity specifies that acceleration of a clock will result in a clock change in reading or clock error. Any examination of the HK experiment must consider the total acceleration of the clocks as they relate to the known universe. Others have disputed the contention that the Hafele-Keating experiment results support Einstein's relativity also. There was a paper in '96 by Spencer and Shama that was presented at the NPA, the third one in Arizona. A website by Kelly, antirelativity.com. He's gone back and reanalyzed some of the test results, and apparently there was some averaging done and some leisure domain, etc., by Hafele-Keating in order to support that the time always slows down. Some of the clocks ran faster. So, I mean, just like with Michelson-Morley, what they report as the results is proving relativity. When someone actually gets down there and looks at the test results, the raw test results, they can come to different conclusions. And the same thing happened with Crothers. When he looked at Schwarzschild's original work, he found out that Schwarzschild didn't predict a singularity, which was hidden for years because he got killed in World War I. Sprague's discussion prompted me to consider the possibility of clocks, not time, showing variation under accelerated movement by postulating 3 examples of acceleration. I looked at a change in speed but not direction, a change in direction but not speed, and then a change in both. As my clock, I postulate a gun shooting a projectile into a target with the time between ejection from the gun and striking of the target becoming the unit of time measurement. Let's begin with a boxcar of length 2, arbitrary units. It has a pair of guns, shown in gray, mounted to fire in opposite directions. And they're located at the midpoint of the boxcar. At time 0, when the boxcar is stationary, both guns fire bullets at equal speeds of 1%. So, time 0, the guns fire. At an infinitesimal time later, 0 plus, the boxcar, and therefore the two fixed guns, is accelerated to the right at 1 per second squared. That's shown by the white arrows here, A0, that's the acceleration. Since both bullets have already left their guns, neither feels the acceleration, so each continues on its path at the original constant speed. After 1 second, the boxcar has traveled 0.5, so 0, here's 0.5 relative to the original position to the right, which also now is where the two guns are located because they're in the midpoint. And their speeds of the guns are 1 per second to the right. Relative to their starting points in the boxcar, the bullets have now reached the following positions. Relative to the boxcar, the first bullet that was shot to the right is at 0.5. The second one is at what would be minus 1.5. And actually, the second one has actually gone through the wall of the boxcar. These are their positions, of course, relative to stationary, they're at 1 and minus 1 because they were launched when the boxcar was stationary. Case 1, acceleration due to change in speed but not direction. That was the boxcar example. When stationary, an observer measures the standard unit of time on the boxcar as that for a bullet to reach a wall, the same for each gun bullet system. If you were on the boxcar and it was stationary, you shoot them off, both bullets hit the wall at the opposite walls at the same time, that's your unit of time. However, now the accelerated observer, assuming equal speed bullets, would conclude a clock calibrated to the upper gun runs faster than one calibrated to the lower gun because its bullet reached its wall sooner, actually passed through the wall, and that the upper clock runs faster than standard time while the lower one runs slower. So the lower one didn't reach the wall. So if he's on an observer sitting on the boxcar after shooting off the bullets and then the car accelerates, he's going to say, oh, the clocks run differently. Acceleration, the direction matters. Acceleration in the direction that the boxcar moves and the opposite direction. The two clocks run differently, and one's faster and one's slower. So I say, maybe this Don Spray has something. Let's continue. Getting to circles. Like I said, now we're going to test my math and geometry. Here we got a carousel, a torus, rotating at 2 pi radians per second. And I put the pi's in there so I can get rid of them afterwards. That's why I have the funny radii here, 1 over pi, 3 over pi. Such that the tangential speeds, v sub t, of the inner and outer rims are 2 per second and 6 per second as shown. The gray gun, which is fixed to the inner rim, with the end rotating at 2 per second, shoots a projectile from point 0, such that it travels at the speed calculated here, 31.89 seconds at an angle alpha, which is confined with geometry, turns out to be about 3.6 degrees. So the gun shoots off at time 0, the torus is moving, so the bullet picks up the tangential speed, and it travels along path OB, hits the outer rim at point B after what I calculate to be 1.0199 seconds. Meanwhile, point A on the outer rim, which was directly above the gun, and the outer rim is going at a higher tangential speed, has reached point A prime. And it is at about 7 degrees from the original point A. So the bullet doesn't hit vertically where you would have expected it to hit at A prime if there was an acceleration. The acceleration here, of course, is circular motion. It's moving the tangential, the angular speed is constant, but the tangential speeds are different, and this is accelerated motion of a circular nature. We're dealing with acceleration due to change in direction, because of the acceleration this way, inward, but not speed. Define a new time unit, the zek. Sounds like second, sec, so I came up with zek, as the time for the projectile to hit the outer rim. When stationary, 1 zek corresponds to 0.02 seconds. And that's just a calculation. When rotating as shown, if I'm on the torus, my zek became 0.197 seconds. Time has sped up by what turns out to be 0.13%. At least that's what we think happened. But really, time hasn't varied. Only the directional acceleration has caused an apparent speeding up by this much. So if we're using the projectile hitting the outer rim as our clock and standardize it when the carousel is stationary and call that 1 zec, we conclude that when accelerated, this clock runs faster. It actually, more time has passed by. Now I'm going to put the gun on the outside and shoot it inward. Same, everything else the same, speeds, etc., etc. Now it's going to travel along path OB. Now its tangential speed's higher, so it's going off at a sharper angle than it did before. Point A on the inner rim, which was immediately below the gun, proceeds to point A prime in this case. Remember, the inner rim tangentially is rotating slower. And that turns out to be 7.6 degrees for A prime, but alpha is 10.67 degrees. Now let's say we define as, again defining the zec as the time for the projectile to hit the inner rim. So when it was stationary, we could shoot the projectile up or we could shoot it down. When stationary, we get the same zec, 0.02 seconds. When rotating is shown, now 1 zec is 0.211 second. Time has slowed by what turns out to be 6%, an opposite effect. Again, time hasn't varied, but only the directional acceleration has caused an apparent slowing, in this case by 6%. And it's not symmetric. I mean, the outer rim's going, tangential speed is higher, so it's got a bigger effect. The slowing down is greater than the speeding up because we're playing with circles here. If we now use the projectile hitting the inner rim as a clock and standardize it when the carousel is stationary, the 1 zec definition, we conclude that when accelerated, the clock runs slower because this is how many zecs we pass by. Again, direction matters. So once again, I'm concluding that Sprague is right. First case, I looked at change in speed. Now I'm looking at change in direction, and both of those are types of acceleration, and in both cases, I found clock can run faster and slower. Time doesn't change, but the clock can run faster and slower because it was accelerated. I corresponded with Sprague, and he was interested in this, and he said, well, why don't you look at an accelerating torus? I don't know, gee. I mean, I had enough trouble doing it, moving at constant speed. Now you want me to accelerate the thing? So I figured, all right, I'll give it a try. Carousel was rotating as before. We'll start with the first case, the gray gun. However, now at an infinitesimal time later, 0 plus. Again, the bullet goes off at 0. 0 plus, the carousel is accelerating. I mean, it's already moving, but at a constant speed, I shoot the bullet off, and immediately after the bullet just leaves the gun, I start speeding up the torus. And so again, I conveniently calculate the acceleration so that I get rid of the pi's and all that type of stuff. So my initial speeds, 2 per second inner rim, 6 per second outer rim. Acceleration inner rim is 2 per second squared, outer rim is 6 per second squared. The projectile does not experience this acceleration because it's already left the gun, and it reaches the outer rim in 0.199 seconds as it did before. Because the carousel now speeds up, it will rotate a bit farther. Before it rotated about 3 to 4 degrees, I have to go back. Now it's going to rotate 7 degrees, such that the projectile now strikes the outer rim at point B prime. This was the case where I didn't accelerate the speed of the rotation. I just had the directional acceleration, and it went to OB. Now the bullet goes to OB prime, such that the projectile strikes the outer rim at point B prime with a perceived trajectory of 0.6404. And it sees my time is going to be different than it was when I wasn't speeding up the torus. When the carousel was not speeding up, the trajectory length was 0.637, required 0.01997 seconds, or that equivalent zecs, to reach the outer rim. Now the length is longer. It's traveling a greater distance, requires more time, and now I have, instead of 1.001, I got 1.009 zecs to reach the outer rim. That is, more time has elapsed, which means the additionally accelerated clock, speed plus direction, now runs faster by what I calculate to be 0.73%. And the symmetric case, not purely symmetric, but now I'm going to shoot the gun inward. I'm going to, as soon as the bullet leaves the gun, I'm going to speed up the torus, and I go through the same set of calculations. And basically what I see is before, this was my trajectory, OB. Now with the acceleration of speed, it's a shallower handle, OB prime, and that's the length. Same type of calculation when the carousel was not speeding up, the length was 0.6738, required 0.211 seconds. Now it's shorter, 0.6409, requires less time, 0.2013 seconds, or 9/10 of a sec to reach the inner rim. That is, less time has elapsed, which means the additionally accelerated clock, speed plus direction, now runs slower by 4.6%. Again, direction matters. So Sprague told me, yeah, why don't you try this? I tried it. It still verified what he was saying. Can accelerating clocks run both faster and slower? Sprague believes so and provides his arguments on his website. He has other examples. He's got the Earth, and he has good examples too. I've just decided to do this on my own. I came to the same conclusion using 3 cases considering both speed and directional changes as part of acceleration. This doesn't imply any belief in the variation of time itself, whether under constant or accelerating velocities, but merely a physical effect on an accelerating clock, not an inertial clock. Nor does it imply any belief that a clock moving at a constant velocity, even near the speed of light, will show any variation. For me, the key is acceleration, and direction matters. And so I ended up agreeing with what I found on Sprague's website. So I said, this pretty much taxed the limit of my calculation abilities. Any questions? Yes?
I thought it was very well done. I had a bit of trouble understanding the concept of clock as in a single one-shot deal. This might be better if you were to say the clock is defined by the length of time it takes to fire a gun is 1 sec, and then when it hits the outer rim, then the next shot is fired. But for purposes of calculations, I will only consider the first iteration, just to get the idea of a clock better, rather than a one-time deal. Because clocks aren't, it takes 1 second, okay, it's done.
Yeah.
It takes a second,
Yeah.
it takes another second.
The stationary could be the stationary case is the thing that defines where you're starting from. So go back and forth, and I can that's even hairier geometry. So
Yeah, that's why you consider the first interval only.
Yeah, actually, I mean, obviously, I can play with the speeds. I had to play with them enough because what was happening is on this case, I mean, if oops. I was finding that if I slowed the speed down too much, I missed the inner rim, and then that kind of destroyed my whole analogy. I mean, I could make the rim, I could narrow it, I could make it bigger. So originally I was going to send it off at 10 pi per second. But I said, oh, then I miss everything, so I sped it up, and it's just so I wanted to make sure I could hit the inner rim. That's obviously if I do back and forth, I'm probably this would be okay because it's going to bounce back there. Yes. Anyone else?
Just a question. Accelerated clocks run faster and slower. You mean a clock will run faster if it is accelerated, and will run slower if it is decelerated?
Not necessarily accelerated or decelerated, though I would think again, it's going to matter in direction. With the circle example, I'm not sure which you would call accelerated. I don't know if there's any deceleration in this case. If you go back to, let's see, here's the boxcar. The boxcar, I mean, if you're treating this as if you're sitting on the boxcar, you're going this direction, you might feel you're accelerating. If you shifted the car in this direction, I think it would just be the mirror effect. So you would see, depending on how you define the clock, it depends how you define. I guess I didn't consider the case if I started stationary. If I was going along at a constant speed and then I slowed the boxcar down, that would be deceleration. And I didn't do the calcs, but I suspect I would get the opposite effect, is that the clock, this clock would then, which was running slower, would then run faster on deceleration, while this clock, which is running faster, would then run slower. So I think whether it's acceleration or deceleration, depending upon if you have a directional clock, which is the examples I had here, you're probably going to experience both. Yes?
A different perspective. Assuming there's ether, and assuming that if an object, proton, or a car or anything else is accelerated and approaches the speed of light, and assuming the ether has substance to it, try to picture this. You have a light rain and you're in a car and you're going faster and faster, and that light rain becomes in effect a wall, because the speed is going so high. And thinking in terms not of mathematics, but physical effect. If you are going at an immense rate of speed, virtually against a wall, is it possible that what will happen to you or your car, or to a clock that is in your car, that it is up against such an immense force that it's not going to work as well? Your clock is not going to work as well, you're not going to work as well, and all the physical processes may slow down.
It's possible.
Might that be an explanation for this idea of not slowing of time?
Right.
Because I'm totally with you, but slowing of the clock.
Could be.
Yeah. Okay.
I mean, like I say, I just toss ideas out there, play with them a little bit. I don't really come to any firm conclusions other than, well, my conclusion here was that Sprague's website made sense to me, that accelerated clocks can run faster and slower.
Yeah.
I don't have the answers. I just ask a lot of questions.
Well, which is all I'm doing here.
This group for 20 years, a common thing that is talked about when it's dealing with this is called clock retardation. And clock retardation is actually a nice term, because what it means, it's very clear that it's not time slowing down. When I talk to an average person, I said, if I take a pendulum clock here that relies a fulcrum, and you're looking for, you have to have that gravitational field to keep it going. You put it up in space, it's not going to do too well. And they sort of get that idea. And then the question is well, if you put if you freeze a person and then you thaw them out 1,000 years, you have the twin paradox, but it's not according to, of course, the theory and what they're talking about with time slowing down, which was what we're all here saying. So that's a common thing that I've heard in this group is called, to talk about clock retardation.
I know. So, I mean, I've had this, when I gave the paper 2 years ago on time dilation, I was talking about, and Dick would have liked this, that it was, the time dilation was perceived, it wasn't actual. And somebody in the audience got up and just said, you're absolutely wrong, time slows down with speed, or clocks slow down with speed. I said, okay. I said, I found websites, he says, the GPS proves this. And I said, well, I found websites that have alternate explanations for GPS, and it has nothing to do with clocks slowing down or time slowing down or anything. So, yeah,
That's used a lot. The GPS is one of the hard problems of why people hold on to relativity. If you talk,
sacred cow.
If you look in the documentary we have that I made, you have Ron Hatch, and he talks about it. The problem the relativists are looking at it wrong. What happens is that it's clock retardation. It's a physical object. Physical objects we make are affected by gravity, because everything that's made out of atoms, at least we can tell, is affected by gravity. So when you take it up into a less gravity field, it's going to act different, even if it's atomic, because atomic structure is also.
And I think Sprague would go along because gravity is acceleration.
Mm-hmm.
So he would probably agree with you.
Yeah.
And I wouldn't have a qualm with that, because again, if I'm an acceleration, I can accept it. Anyone else?
Is that it?
Like I said, this is the most complicated it's going to get.
Okay.